And recording is officially rolling. So welcome to the last day of August, Tuesday, August 31st. And we're going to take today to wrap up a bunch of linear motion stuff. I want to do as many puzzles as I can with you guys, to solve as many problems as we can. So I started putting you guys' next quiz together, which is going to encompass both linear motion and projectile motion. We'll start on projectiles tomorrow. Right? And tell you guys that it's going to be pretty challenging. Just like last quiz, I told you what's going to be on it. So this one, there's going to be some graph stuff, maybe kind of similar to what we're doing here. But you have to use your imagination. This is going to be a take-home quiz, so could be that much more challenging. There's going to be a bunch of problems like solve in terms of variables, but we'll get all that practice in today. We're going to really solidify your guys' linear motion knowledge. Yeah, come on.
So what's the take-home quiz? You can take it home and...
Yeah, so I'm mostly finished with writing it. I'll give it to you guys next week. So probably like around the end of next week, I'll give you guys a quiz. You can take home over the weekend. So this will be, it's going to be on both linear motion, which we're going to solidify the information for that now, and also projectile motion, which we're going to start tomorrow. Okay? All right, so we got create graphs for the following scenario. A ball is thrown downward from the top edge of a cliff. Okay? X versus T, B versus T, A versus T. Hey, this is 3 classic graphs. Okay? Let's call it down the positive direction. We've been doing that all along. Some of you guys, I see you've been looking at your AP progress checks, right? Which are due a week from now. Yeah, a week from now. And we'll go over this next week. And sometimes AP says down is positive, like we've been doing. Sometimes AP says up is positive, but you guys can feel that, right? Just turn everything upside down. Right. So I'm going to just recreate these 3 sets of axes. I'm going to blow them up bigger while you guys are writing in this graph. Hopefully you guys already have those axes.
Mr. Griffin,
Oh, yeah.
is there a difference when it says thrown compared to drop?
Yes. Yeah. You guys see the word thrown? Right. That is definitely not dropped, right? Because if you throw something, then when you're releasing it, is it already on the move? Yep. And that's different than dropping it. So it's definitely not from rest.
Okay, what?
Right. So throw ball downward from cliff up. Right. Down is the positive direction. Right. And we're looking at, okay, so time is ticking along for every single one of these. From left to right, time is progressing, right? It's like tick. Right. How far did the ball go in meters? How fast is it going meters per second? And what's the acceleration meters per second squared? Right? Like that. Right. Let me give you guys a quick recap of some similar type scenarios you saw in the past. Okay? So I'm about to show you stuff that's not exactly this, but it's kind of similar. Okay? And in fact, if you're in class, you guys see these 2 posters over here? Okay, I'm going to go over some notes that are pretty much those posters. Okay? You guys remember we started with just dropping a ball off a cliff? It looked like this. Okay? So velocity versus time starts from rest at time 0, and then increases speed at a constant rate. And that constant rate is the rate of gravity, free fall gravity. Okay? And remember how far it falls? It like spreads out over time. And on a position versus time graph, that makes a what shape? Parabola. And wouldn't this right here be the vertex of that parabola?
Yes.
Yeah, that's true, as long as you drop it. So the word drop is key, right? What's that? Right. Then after that, we did, well, what if you throw the ball upward? And again, not exactly what I'm having you guys do right now, but this is, you guys saw this a few days ago. If you throw it upward, if down is positive, then isn't up the negative direction? So you're throwing it into negative territory. I'll start with the middle graph, just like I usually do, velocity versus time. So as you're releasing it in the negative direction. It's already on the move in the negative direction, so B naught is negative. But as soon as it leaves your hand, it's in free fall. So it's accelerating toward Earth at the rate of g. So we get a straight line like this, right? Okay. You guys remember where it crosses the axis here? That's where the ball is turning around. That's like this point up here, right? Okay. So 0 velocity for that one moment. That represents the peak, right? That's why I did a little dashed line right here. So on the X versus T, that's the peak right there. Okay. In fact, isn't the area of this triangle, you guys see a triangle right here? What does the area of this triangle represent? The maximum height. Right? Let me put that in my notes. This is H max. That's this area of this triangle. So we're trying to hash this in. Right? Is that? And then, okay, so free fall, still just rate of gravity, right? In fact, if all you had was the acceleration graph, you wouldn't necessarily know like which way you threw it or which way the ball's moving. You just know it. Right? Now the new situation. You're going to throw the ball downward, so you're throwing it in the positive direction. Right? Look, you guys ready to make these? Or maybe you guys already have the graphs drawn, and if you get it wrong, you just erase it. Because guys, if you can beat me to the answer, then you should have confidence that you know how to do this. Right? What does your guys' V versus T graph look like?
Is it just a
It's
straight
got
line
to
that
have a
starts
point in
like higher up?
Straight line with a wide.
Yeah, so.
Boom, just like that, right? You guys are saying? Okay. And what can I call this right here? Yeah, initial velocity. Good call. This would be at time 0. Starts right there, right? Okay. It's already on the move. Okay. What is the slope of this line? G, gravity. Yeah. Right. It could go like right here, and then you could also create acceleration versus time. So everybody's got that so far, right?
Yeah.
Right. So the slope of this represents this guy's coordinate. Right. All right. Now for the one that's tricky, position versus time. Now you guys have done enough of these that you know, anytime there's a free fall situation, we're looking at vertical motion, or any kind of uniform acceleration, over and over again, position versus time is what shape?
Parabola.
Yeah, a parabola. So this is going to be some slice of a parabola, but can you guys figure out exactly what size of a parabola it's going to be? What do you think of it?
I think that what we're going to do is we're going to go just move the X part of the vertex further to the left on the parabola.
You're right. Yeah, good call. Yeah. All right. So, let me do this. Okay. You guys see at the origin here? Let's define the top of the cliff as 0.0. That's kind of arbitrary, but that's a common thing to do, right? Top of the cliff is 0.0. Okay. Do this. Put a little dash that's like at a slope. It's just like inclined, like at an angle. Right? And that is going to, the parabola is going to be tangent to that at that point. So it's going to go like this. So that definitely is a parabola, right? I'll even spell it out. It's a parabola. Okay. But if you listen real close what Eddie was saying, is the vertex at 0, 0? No. Right? Mathematically, the vertex is probably right about here. Like if I finish the parabola, it'd have to like sweep around like this. The vertex might be about right here, something like that. Okay? Which gets back to this dashed line. This dashed line has a slope. Who can figure out what the slope of that dashed line is? That's tangent, pretty much at the origin point. Velocity. Which velocity? Initial velocity. Right? And if you didn't know, then think about units. Isn't slope rise over run meters per second? So this is initial velocity. That's exactly what this is right here. Okay. Is that? There you go. That's it. You did. Now, some other stuff I want to say about this though. If you go from the top down, it has to do with slopes. Like this instantaneous changing slope, well, actually changes at a constant rate. Changes at this rate. Okay. This one has a constant slope, so this one has a constant coordinate. Okay. But then you can also go backwards. You go from the bottom up. Okay. Oh, who remembers? Choose blue. For some time here. Okay. I'll call it some general time t. Okay. So, like that. Make sure I got you in here. Oh man, it didn't work. I'll do this manually. That's good. You're good. I got you. All right. Just remember what property of A versus T leads you back to B versus T? The area, right? And think about it in terms of units. If you ever forget, just think how units work. You can figure out like a bunch of different graphs this way. It has a height in meters per second squared and a base in seconds. What happens when you do meters per second squared multiplied by seconds? Doesn't one of the seconds cancel? Leaves you with meters per second. Okay. Yeah. So this represents. I'll call this the change in velocity is really what it is. Right? It's like acquired velocity, and it is GT, isn't it? Right? It's like this hatched area right here, this here rectangle. Right? Now, why did I put that triangle there? Right? I'm just trying to add a little bit to the class at a time. Right? that means change in. You guys know that? Like the triangle is the Greek letter delta means change in, right? Because here's strictly what it tells you on this graph, okay, which I think you may have been able to figure out if you put two and two together, but it's sort of the first time I'm explicitly telling you this. It actually represents this change right here. This is delta V, change in velocity. It's like acquired velocity. Because if you think about it, if all you have is the acceleration information, which is like this flat line, okay, so gravity's pulling down. Okay. Does that tell you anything about how fast you threw the ball? You have no idea. You could have dropped it or thrown it down or thrown it up. This graph looks the same anyway, right? What it always tells you is this change right here. Okay. In fact, I could sort of split this up into two different shapes, couldn't I? See, this trapezoid is actually like a triangle sitting on top of a rectangle. You see it? Triangle sitting on top of a rectangle. Okay. And what property of v versus t leads you back to x? Also, area has a height in meters per second, a base in seconds. Well, if you do that, meters per second times seconds, you get back to meters, right? All right, you guys ready to have your mind blown? Ready for this? Everybody's brains are on, right? Right? I'll show you something really cool here. What is the area of just the rectangle? Just the rectangle. What's that? Isn't it v naught t, right? Base times height, right? Get that? So that's that rectangle. What is the area of this here triangle? Well, isn't the area of a triangle 1/2 base height? Okay. And the base is some value t, going 0 to t, right? And the height, well, that's delta v, but hey, isn't delta v just gt? Right, gt, that's how we got that, right? So the height is gt. Hey, could I combine those t's and call that 1/2 gt squared? Hey, that looks a lot like college. Right. Got the ball for 5 seconds, got 125 meters. That was that one, wasn't it? And if you put it all together, so this triangle is 1/2 gt squared.
Where'd you get the GT from? Okay.
This right here, the area of this rectangle is base times height, right? G times t.
Yes.
That represents the acquired velocity, which represents the height of this rectangle, this triangle.
Okay, I get it.
Yeah. Okay. Yeah. So, good question. So put it all together. You guys see a giant trapezoid underneath that v versus t curve? Giant trapezoid. What is the total area of that trapezoid? V naught t plus 1/2 gt squared. That's exactly the first amigo. Yeah. Guess it. All right. All right. So rest of today, I want to solve one of the problems off this page with the boxes just in terms of variables, because that's a really good skill to have in AP and also upcoming on the quiz. I'm telling you guys what's coming up on the quiz, solve in terms of variables. That's one of the things they do. And then after this, we'll do a bunch of book problems, as many as I can do. You guys see number 3, number 4? So that's one scenario.
The worksheet is this?
This is linear motion.
The old
Linear motion, the page with the boxes on it. Says, a ball thrown toward the ground from a treehouse. Hey, you threw it toward the ground from a treehouse. Didn't we just do the graphs on that? This is that scenario, right? From some given height, so we know the height of the treehouse, reaches the ground some given time. So somebody brought a stopwatch, we timed this thing. Can you find the speed that the ball was thrown and the speed that it's hitting the ground? Now, in the way I set these boxes, I explicitly give you, right? Here's measured time for the ball to reach the ground. Here's gravity pulling. For the notes, I'll run that to 10 meters per second squared. Typed at 9.8. Okay. And then here's the height of the treehouse in meters. I don't know how fast this guy was throwing the ball, and I don't know how fast the ball was landing on the ground. Okay. But I bet in principle we can find those things because we have 3 kinematic values. That's how these work over and over. Okay. So, like I said, I'm going to solve this all in terms of variables, and this is a skill that you need to have. So if you're super rusty on this, then go home and you guys got 20 practice problems right there to do this. Okay? So this is number 3 and 4 on the page with the boxes. Have a tree house. Got this ball. It's being thrown down at some unknown initial velocity. Right? How fast is that? Don't know. It's going to hit the ground. Hey, when it does hit the ground, now this is many steps ahead in the future, but if you were to plug in some numbers, would you guys agree that V final better be greater magnitude than V naught? Right? So if you have numbers and you're plugging in numbers, then make sure little details like that make sense. Check out that everything should be self-consistent in physics. Right? Let me make a tax VV checklist. tax dv. Okay. The height of the tree, I could call x. And let's say that that is a known quantity. So do a little bing, like we know what x is. Okay. Oh, you know that Earth gravity is pulling down at 10 meters per second squared. I'll just very generically call that g. So bing, we know what a is. I'll say equals g just for the notes. I'll call that g in my notes. Okay. And there's a guy down here with a stopwatch, and he's measuring how much time has passed. Bing! Is that three things? Okay. So this guy here in the treehouse, maybe we should draw him. Okay. So he just chucks this ball straight down, and we don't know how fast he's throwing or how fast it's hitting, but we do know how far it traveled by the treehouse. We know the rate that it's picking up speed, Earth gravity, and this guy timed the whole thing. Right? Is that? Okay, so how are we going to figure out how fast did the guy throw the ball and how fast is it crash landing? Okay, we'll handle those one at a time. All right. Now, here's your guys' formulas. Which one looks like it's going to solve it for us? First, second, or third?
First.
Guys like the first one? I like the first one too, because we have everything in the first one except for V0. That's one unknown. One equation, one unknown. Perfect. Versus, see if you pick either of the other ones, see how there's two unknowns there? You would run into a dead end. There's two unknowns here, dead end. I guess you could do a system of equations with these two, but that would be really long and complicated. Yeah, the first one is definitely the fastest way to solve it. Let's do it that way. Oftentimes, there's multiple ways to approach these, right? But you guys pick the best way. So, think of that. V naught t plus half at squared. Right. Right. Now, notice I haven't given you guys any numbers. Can you guys solve for the throwing speed based on just variables? See if you can beat me to the answer. Right. You guys already picked out that equation, which is the best one. Can you guys beat me to the answer? Let's see. Not t is, I have to subtract over the half at squared. Oh, I meant to call that g. Sorry about that. Half gt squared. I don't know. I guess you could call it a. Doesn't really matter. Right. Then divide both sides by t. One of these t's cancels. That's it. That's the whole thing. So boom. That's the solution. That's the general solution. So now, see the power of doing something like this is that you could have any tree house of any height. You can have any time show up on the stopwatch. And for that matter, you can even switch planets if you wanted to. Because, gee, right? And you can always figure out what the throwing speed is based on completely generic situations. Right? Oh, real fast, plug in the numbers that are on my paper just to show you that this does work out. So on my paper, I have a tree house of height 8 meters. The time to reach the ground was 0.7 seconds. Say minus 0.5 times, say 9.8 meters per second squared times 0.7 seconds shows up again. Right. So according to my numbers, V0, the throwing speed should be pretty much exactly 8 meters per second. And I have an answer choice that says exactly 8 meters per second, 8.00, get like 7.999. Yeah, okay, that's that. Right. That's it. All right, so that definitely worked. But we got to know one more thing. How fast is this thing hitting the ground? And for that, what do you guys feel like? First, second, or third?
Second.
I like the second one too. Now, you could use the third one. That'd be fine. But the second one's more straightforward because the third one, you have to do like a square root. So yeah, let's definitely do the second one. That's a lot more straightforward. Second equation. Let's go. Final velocity equals initial velocity plus, well, acceleration times time. So let's call it GT, right? Because G. Yeah. Okay. And you know what? We have V0. It's this entire expression right here, isn't it? Isn't that what this is right here? That's just that, isn't it? Can you just substitute that in? Substitute. Okay. Solve for crash speed. And that's going to look like, what is that? X over t minus half gt. That's that. And I got this plus gt tagged on the end from here. Isn't that true? Is that the same thing? Okay. I can drop the parentheses. Get rid of those. Scribble, 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 scribble. Okay. And then, hey, see I have GT. Let's refer to that as a pizza. I have a whole pizza here minus half a pizza. Guys, what's a whole pizza minus half a pizza? Half a pizza. So doesn't this whole thing just become final velocity is equal to, okay, so it's still at the x over t part. Okay. Plus half of a pizza, like that. There you go. Now you know how fast the ball is hitting the ground. Right? Guess that? You guys can solve in terms of variables? Right? Let's compare these two. Because remember I said final velocity better be greater magnitude than initial velocity? Right? Well, it looks like what's going on is that initial velocity was like x over t, that could actually be called average velocity, couldn't it? Average velocity minus some quantity. And the landing speed is the average velocity plus some quantity. Hey, definitely has to be faster. Just even without any numbers, you can still confirm that. Guess that? You guys ready to do some college physics? I think we're sufficiently warmed up. Where's my college physics? This here. Here we go. All right, so I'm going to create some problems that are really similar to some ones you guys have, so that you guys can actually use the actual college problem to have a little bit more practice. I'm going to do one that's very similar to number 24. I'll call it number 24, but it's going to be slightly different. Okay. Number 24, they give you a velocity versus time curve, and they ask a bunch of questions about it. So I'm just going to make it my own, right? Maybe there's, so yeah, velocity versus time. Okay. Trying to think of a situation that's going to work out for me. Maybe something like that. Okay. Maybe this is a car. It's driving on a road, something like that. Okay. Well, let's attach a story to this car before we do any other kind of analysis. Okay. What could be a story for this car? This car starts by doing what? It's going constant velocity, right? In fact, by the time we start paying attention, it's already in motion, isn't it? Right. So it's already been in motion. It's just cruise control, right? Then this guy does what? Yeah, hits the brakes, slows down, comes to a stop, right? Looks like he stopped for a while. Then what happens? Yeah, puts it in reverse. Now he has to speed up a little bit to get it to this. But then it looks like it goes constant velocity backwards, right? And then slows down, comes to a stop again. Anytime velocity is 0, that refers to the car being at rest, right? Right, guys, that? Okay. How about this? Between where the guy started and so at time 0 and where he ended up, is he overall more forward or more backward? Or did he end up at the same spot where he started?
I'd say
More forward. How do you know he's more forward? Look at this trapezoid compared to this little tiny trapezoid. Is this a huge positive area? So that represents a huge distance forward. Now here he's backing up, but it's only a little tiny area, so it's a little tiny number of meters. Right? But your book asks questions more like this. What does the slope represent? Instantaneous acceleration? Or in this class, I just call that acceleration. I just call it acceleration. Okay. But your book is trying to distinguish between that and what if you went from, call this like T2 maybe, like T1, T2. Right? What if you went from time 0 to T2 and you looked at this here dashed line? That line also has a slope, which also represents an acceleration, right? Okay. I should have changed color. Maybe I should have done blue with that. Okay. Sky blue. Okay. This also represents an acceleration, but it's not instantaneous. See, I picked 2 points and I connected them. What do you think that's called? That's called what kind of acceleration? Average. Average acceleration. Right? Is it? Right. And then, well, I talked about distances verbally, so yeah. You guys got that? You guys good? All right, so if anything like that comes up, all right, I think that's all I want to talk about with that one. All right, this next one, super fun. You guys ready for a super fun problem? You know, when I say fun, I mean fun. All right, number 35. So this one's got the bottom left corner of the page. Okay, again, I'm going to change that to make my own scenario, but it's going to be very, very similar to that scenario. Well, I want to solve this in terms of variables. That's what I want to do. I want to solve this in terms of variables. Okay? So here's what's going on. I got some car A, calls car A, right, that is zipping along with some initial velocity, initial velocity of car A, okay, forward. Okay? And this whole story about like entering a one-lane tunnel. One lane means you can't switch lanes. All you can do is like go forward, stop, or go backward. Okay? And happens to notice that, oh boy, there's a slow-moving van like right in front of the car. So I'll call this vehicle B. Okay? Vehicle B is going much slower. Called this V sub B. Okay? Now notice how, okay, I got VA and VB, right? But VA, I actually put V not A. You guys see that? And the reason is because as soon as the driver in vehicle A notices the van, the slow-moving van, slams on the brakes and that velocity starts changing. Okay? It's going to slow down. Okay? Now there's some initial distance between the front of car A and the back of van B that I'm going to call D. Maybe I should call it D naught just to emphasize that it is a fixed, it's a fixed value. It's the fixed initial distance between the two. Right? And the driver in car A is trying not to hit car B or van B. But the only way to do that is to slam the brakes and just hope for the best. Right? And the question actually in the book is, do these two cars collide or not? Right? Now let's think ahead. Even before I set up equations, think about what would go into this. As if they were to collide, that means they're at the same what at the same what? Same place, same time, same place, same time? I wonder if this is going to be maybe some kind of system of equations where maybe we can determine like position as a function of time for each vehicle and just set those equal to each other, right? Then they would be same place, same time. That would assume a crash. You can figure out from there, right? There you go. Let's try that out. Let me get my, let's just make sure this is pretty. Okay. All right. I want to throw in another detail that vehicle A is accelerating backward, so I'll put a backward arrow and call that A. So that could represent like an acceleration vector. Okay. Now it's only acceleration of car A, but I'll just call it a solid A. Okay. Is that? Okay. Backward. All right. Now, before I can get rolling too far on this thing, I want to mention a detail that I sort of mentioned in passing before, but I wanted to save it for a time like this. Okay. You guys see AP's equations right here? First three. Oh, it's the three amigos. And they actually write these slightly differently than I do, but there's a reason I taught them one way. Okay. And then, I want to specifically focus on, side note before I get where I really want to talk about. See how they threw in some extra subscripts? They've got like X subscripts. They're referring to a specific axis, like a specific direction. We're just doing linear motion so far, but starting tomorrow, we're going to look at like right, left, and up and down. So we might have like an x-axis and a y-axis. Okay? So they're just specifying axis. But you guys see this one, x equals v naught t plus half a t squared? They throw in an extra x naught. And I want to show you what their perspective is, which is a little bit different than mine. Okay. When they do x equals x naught plus v naught t plus half a t squared, okay. Also they throw in some subscript x's to denote a direction. Okay. But besides that, okay. These x's, and this is how AP writes this, refer to exact positions. Exact positions. Right? Okay. How I've been writing this equation looks something more like this. I just been saying x equals v naught t plus half a t squared. Right? Is that? But if I do that, x is not strictly an exact position. It's actually a what represents like a displacement. It's like acquired position. Or maybe it could be your final position with respect to 0 if you started at point 0, which happened a lot, right? But sometimes this is actually written like this. Some people actually throw a little delta there, which you guys saw earlier today, meaning like a displacement. Right? I usually just say X, I've been typing X. Okay. You guys see that? You guys can take what you've learned so far and expand on it a little bit. Okay. Okay. And I'm doing this too because this particular problem we're about to solve, actually it's pretty handy to think in terms of the way AP hands you the formula. Okay. Okay. You guys ready to go? All right, so where's my, oh, it goes here. Several layers deep. Okay. So let's make a position equation based on time for each of these vehicles. So for car A, wouldn't it go the position of car A is equal to, and see if you can construct these before I do. Okay. Wouldn't it be the initial speed of car A times however much time's passed, minus 1/2 AT squared, right? Because the fact that this guy's hitting the brake, slow it down, that's why I did minus, right? Okay, so A itself will be a positive number so that you're subtracting it off, right? Okay, T is how much time driving for. Also, the only vehicle accelerating, slowing down, say, is car A, right? What does the position function look like for the van that's just going constant speed, constant velocity? Can you guys do that before I do? Isn't it just the speed of the van times however much time has passed? Okay. But here's where that last detail comes into place. Okay. These two vehicles do not even start at the same spot. You guys see this fixed initial distance between the two? Okay. Which of course is going to shrink over time, right? Okay. How should I incorporate that? Yep, add it in. Say the van actually started at a location that was some distance ahead. Okay. That's not the only way to do this. You could also say that you could do this in terms of displacement and say the difference between XB and XA, well, this minus this is equal to D naught. That's another way to do it. Okay. But what do we have and what do we want to know? Right. So suppose you were given the speed of each vehicle. You know the slowdown rate of vehicle A. You know the starting distance between them. If they were to crash, let's see, that would happen sometime in the future, which is not yet known. And they each would have traveled some distance. Guys, I have how many equations? Two. And how many unknowns?
2, 3. It's like 2 per.
I think you're on the right track. 3, except that if they crash, they're at the same what? At the same what?
Same place, same time.
Same place, same time. So if you assume a crash, then wouldn't this also be true? Right. And that's 3 equations, 3 unknowns. Can this be a giant system of equations? Right? Yes, yeah. We're also solving for these, I guess. XA and XB. Okay, is that? All right, no, this assumes a crash. Assumes a crash. Put that in parentheses. Okay. Because they would be, right? See, it is possible that this never happens, right? What if A is going slow enough or can brake hard enough that the two vehicles are like, and then they never actually crash, right? Then this will never happen. And I bet maybe you would get something that was like no solution or something along those lines in your math. Let's see. I bet I can put these all together. Star, star, star. Let's bring them all together. One giant deal. If XA is equal to XB, can I just take this and set it equal to this? Here's XA, here's XB. They're same place, same time. So could I say the initial speed of object A times the time minus 1/2 AT squared is equal to BBT plus the distance between them, the starting distance, I should say. Isn't that true? Not the only way to approach to get to that point, but there's one way to get there. Right? Maybe you use your creativity and thought of a little bit of a different way to get there. Right? Uh-oh. Do you guys see a T squared and a T and also another number thrown in the mix? What's about to pop up here? Quadratic equation. Good call. Okay. Let's throw this on this card. Now, this is something that's good to memorize. I mean, if you guys are going to have a take-home quiz in a couple of weeks now, then it's open to something like that. You guys could just Google what's a quadratic equation. Good to know. You guys know, if you have something that's in this form, I'll say AT squared plus BT plus C is equal to 0, remember, if it's specifically in this form set equal to 0, that you can extract t, it's squared there, it's just regular t there, and then got another constant. Let's say negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. You guys remember that? Right. So I gotta do a couple things to get the time. I gotta put it in this form and then apply quadratic formula. You guys remember that? Right. That to the side. Right. I'm gonna rearrange this. So 1/2 a t squared. Add this over. Okay. I'm gonna okay. That'd be plus vbt minus va naught t. Save a little bit of time. I'm gonna factor the t out and do a couple of algebra steps in one here. Plus d naught is equal to 0. Okay, something like that. Okay. And then, hey, we have it in that form: something t squared plus something t plus d squared. Right. You guys see that I can extract t by saying t equals negative b. That'd be negative bb minus ba naught. Or b naught a, b naught, same thing. Plus or minus square root of b squared, so that's bb minus va naught squared minus 4ac. Ooh, just fits in there. All divided by 2a. Isn't that what that would look like? Okay. Remember, I haven't given you any numbers at this point. This is just a very generic, like you could plug in any speeds and any braking acceleration, any starting distance between the two. Right? Get really a bunch of different possibilities, couldn't you? Right? How I want to finish this off though is say that if you had some numbers, couldn't you just run the numbers and figure out some time? Okay? Now, some things though. There is a plus or minus. How could you interpret that? Right? Here, there's my two vehicles. Right? Suppose there are not actually vehicles. What if they're ghost particles? Can you guys imagine that these two might? Hello, Mr. Griffin. Oh yeah. I don't see him in class. Luke, not in class, right? There's no Luke in here. Yeah, maybe he's not made here yet. Okay, sure. Yeah, thanks. All right. What if these were actually ghost particles and they're allowed to cross through each other? Because in physics that could happen, right? They could cross through each other. Could something like this happen? Like something like that? Now, which one of those would actually refer to the crash? The first time or the second time? The first one, right? And would that show up as a minus or a plus here? That would be the minus one, wouldn't it? Right? So the minus one is the one that would actually indicate the crash, right? Also, what about this? What if they never crash? Is it possible you could maybe like make this distance like a kilometer and they just like just never even touch each other? Mathematically, how would you know that happened? You'd be taking the square root of a negative number. Yeah. In fact, if they just barely touch, just like barely tap, you could probably set this quadratic equal this just the square root part equal to 0 and like figure out exactly the conditions to make that happen, right? You guys see, there's like so many ways you could go with this, right? Right. But just to finish this off, your book actually did give you numbers, so I just want to show you the solution. You guys have taken a look at these solutions, right? Look, half a page, boom, whole thing done. Time is one of these two numbers. You guys know it's actually the smaller of the two numbers because that's when they first crash. The other one is just like ghost particles. So, right? Yeah, and then once you get the time, you can go back to either one of these, just plug in t and get x and figure out exactly where they would have crashed. You guys got that? You guys good? Next one. Luke. You said they want you to get back down to the office. Yeah. Hey, Mark, I'm recording this though, so it'll be online with your cameo. Let's do number, number 60. If you look real close, number 59, number 60, 59, 60 are the same situation. One, they give you numbers. One, they say solve in terms of variables. Well, let's look at the variables version of this. So number 60, check where, just in my, check that here. Check out. Number 60, the situation goes, actually, how much? Oh, we're actually doing all right on time, aren't we? Yeah, we're doing all right. Okay. Here's a scenario. There's this guy down here on the ground, and he's got some keys. I'm going to change that to a baseball just because it's a little better. Okay. He's going to throw it to someone up in a building. Right? There's somebody up here, just like they're looking out the window. I don't know why that would terribly drawn, but you guys, right? So this guy's reaching out the window, right? And he's trying to catch this baseball, right? Something like that. Right. Now this guy throws it up with some initial velocity to get to him. Call that V naught. Right? Of course, gravity's pulling down the whole time. Maybe call that G. Right? And I'm thinking that there's actually two different ways for this guy to catch this baseball. Right? One way would be the baseball goes straight at him. The other way is that you can actually overshoot going up and it comes back down and drops and he catches it coming back down. Right? Would you guys agree? You've probably been in this class. You guys kind of feel that it's going to be the same speed either way. Just one's going up and one's coming down, just based on symmetry and having seen so many of these. Right? That'd be true. Right? Forget what they gave here. Right. So. Take a little taxi view checklist. Here's what we know. We know the height of the window. So from where he's throwing it, I'll call that X. Right? So X is a known value. We know how far up the baseball's going. Right? We know how much gravity's pulling down. Let's call it equal to G. Right? 10 meters per second squared down. Right? And let's say that they also brought a stopwatch. So we also know how much time it takes to get from here to here, right? And again, it's kind of interesting. There's actually two paths, right? It could be a direct path or it could be like the log path that comes back down. Right? Two possibilities. I bet there's going to be something quadratic in this, just like the last one, right? Or possibly. I don't know. Right? But the questions are, can you figure out how fast this guy is throwing the baseball and how fast the guy is catching it based on these three known quantities? Right? Can you do that? Which equation do you guys want to start with? First, second, or third? Yeah, I like the first one also, because that's the only one that has both the, okay, you're actually work. Okay. It's the only one that has both the X and the T in it. Let's do that. Good call. X equals V naught T plus half. I would change something. In general, it's half AT squared, but I want to modify this. I'm going to say X equals V naught T. He's throwing it up, the gravity's pulling down. So let's call it up positive and down negative, just to, why not? Would this be minus 1/2 GT squared? Is that okay? All right, guys hit. And we got to solve for V naught. Because, well, it's one of the things we're solving for, right? You guys picked out this equation, good call. Right. Hey, can you guys solve for that? Can you guys beat me to the answer? Let's see, the V naught T is equal to X plus 1/2 GT squared. Add that term over, divide both sides by T, and the throwing speed equals X over T plus 1/2 GT. Actually, this looks really similar to something that you guys solved earlier today, doesn't it? That looks extremely similar. Right? Hey, throwing speed versus catching speed. In this case, which is the faster number, the throwing or the catching? Doesn't he have to launch it up there really fast? By the time it gets up to him, it's going to be going slower?
Yes.
Yeah, and that's true whether it's a direct throw or the lob, either way. Right? This looks like the faster version, right? If you think about what we did earlier. Let's do another equation. You guys remember final velocity equals initial velocity plus AT? Or sorry, AT. Except I'm going to do this. I'm going to say minus GT. You guys are going to go on up positive, down negative. Gravity's pulling the opposite way. It's going to slow it down. Right? You're going to take this whole expression, sub it in right here. We basically did this earlier, didn't we? Right? So you guys got sort of a college problem already. Right? So final velocity, I'm solving for now, is equal to X over T plus half GT. That was all subbed in. And I still got this minus GT here. let's see, half a pizza minus a whole pizza. It looks like I'm in debt half a pizza.
Yes.
Over T minus half GT. Yeah, that looks a lot like what we did earlier, right? And notice the throwing speed is definitely more than the catching speed because it's x over t average velocity plus a term versus x over t average velocity minus some term. Guys good there? Okay. How about, let's look at number 72. Okay. It says, this one has to do with ultimate test of a young man's career. Actually, I remember this question from when I was in high school too. I don't know if I was using the same book. It's too long ago for my memory, but I do remember this question. So, number 72. Okay. Says something like this. Right? So there's this bridge. Gives some of the history. It's like this 400-year-old bridge. Right? Then we got cliff. We got a river down here. Right. We got like a shark. He's just waiting. Right? He's a happy shark. Right? And a couple of guys up here. Right? Now we know the height of this bridge above the water. I'll call it X. Yeah, I guess I'll just call it X. Right? Want to be more creative? I guess you call it A or something, or H. Right? Right. So there's the river down here. Right? We know gravity's pulling down, so I'll call it G. That'd be downwards. It's a little vector. Right? If this guy just barely steps off the bridge, what is his initial velocity? 0 meters per second. Right? Hey, that's like 3 things, isn't it? Right? So if you make a little checklist. I know this is 0 meters per second. I know acceleration is just g. And I know the height of the bridge, but let me just call that some generic height x. Right? Whatever. And the question is, just after this guy stepping off the bridge, right, it's going to take some time for him to fall, and he's going to splash in the water, like a splash. Like, wow, there's a shark. And then there's going to be some time for that sound wave to travel up to this to his friend up here, and his friend's going to hear the splash. And the question is, what's the total time? What's the total time between falling and hearing the splash? Right? Well, what's going to take more time, to fall or for the sound to return? Yeah, it's going to take more time to fall because sound moves really fast. Also, when we eventually get to the sound part, is sound under the influence of gravity? Does sound bend with gravity? No. No. So sound's just going to be distance equals speed times time. It's just going to be right like that. So if we want to figure out, it looks like see if I want time and I know the height that he falls. This is going to be the first equation probably. Okay. So I'll start here. X equals v naught t plus half at squared. Right. Now I'm going to modify this a bit. Right. So this x, of course, is the height of the bridge. That's that. Okay. This piece just goes to 0 because from rest. Right. So x equals. Okay. This a, I'm going to call it g. And this t is really the falling time. I'm going to specify that because later on, we're going to also have a time for the return trip of the sound. Right? Okay, can you guys solve for the falling time based on free fall gravity and how far? See if you can beat me to the answer. Maybe 2x over g is t fall squared. Square root both sides. T fall is the square root of 2x over g. Okay, is that what you guys got? Okay. Now that's not the final answer yet, but that's an important part. Maybe we should dash that. Okay. That's part of the answer. So now, if we know the height of the bridge, we know what planet we're on. Hey, we can even switch planets, couldn't we? That'd be fun. We can figure out just the falling time. Now, it's also going to take some time for the sound to return, right? Can you guys just use distance equals speed times time for that part? Right. This is now this is the speed of sound, and this is the time for the sound to return. But it's the same x. Right? You guys get it? Now, can you guys solve for the return trip of t? Or yeah. So t sound. Well, it looks like it's gonna be, you just divided the speed of sound over, right? Isn't it just the height of the bridge divided by the speed of sound? Right? So hold on to that. something like that. Is that true? Right. And now, to get the total time, right, between this guy just barely stepping off the bridge and this guy hearing the splash sometime later, right, don't you just have to add these two parts together? Do something like that? Yeah, that's exactly what we'll do. Let's do, so T total is the falling time plus the return trip of the sound. So T total is, okay, well, we have an expression for the falling time. It's the square root of 2 times the height of the bridge divided by the gravity pull. And we also have an expression for the return trip of the sound. It's the height of the bridge divided by the speed of sound. By the way, in case you were curious, the speed of sound, put down here, V sound, is approximately 340 meters per second. That depends on temperature and pressure conditions, but it's called about that, right? If you wanted a number, right? Yeah, that's it. That's the answer to this this question. Right? Well, this is the general answer in terms of variables. Right? Now, your book actually gives you specific numbers to plug in, but again, I want you guys to have the skill as AP students to be able to just solve in terms of variables. See, you could have any bridge height, pop it in for X. You could even change the speed of sound if you wanted to. Maybe we're changing planets, so we've got different gravities. Maybe the new planet we're on has a different atmosphere, so sound travels, different speed. Right? Here's the height of the bridge in 2 different spots. Right? And you have a generic way to figure out how long this guy's waiting to hear the splash. Right? You guys see that? Right. So, per usual, you guys have all these college questions. That's lots and lots of practice problems that all have solutions. Here's all my solutions. I printed them out, but they've been on Classroom for a long time. If you guys want even more questions, you guys got the ones with the boxes. You guys have the textbook you have access to. It's got more questions that I didn't make the solutions for, but if you want to try some out on your own. Right.
Mr. Griffin,
Can
you show
yeah.
number 35 again?
Number 35.
Those look like the cars.
The one with the cars.
I
yes.
just wanted to see like the final answer.
Okay, yeah, I'll take you guys through a walk through this. Now, I didn't actually finish it out on those notes, but
I got like negative 13.6 or
Here.
something. I don't know how to apply
yeah, you should get positive numbers because if they do crash, it would be some time in the future and some distance in the future.
Okay, is the number
Yeah. So, wait, you guys stop the recording here and I'll walk over and take a look at what you got there.